Hello, and welcome to today's lecture. The topic will be single sample tests. Okay, so in this lecture, we are going to focus on hypothesis testing in situations where we are comparing a single sample to a known population. So, for example, maybe you want to know if PhD students experience more stress relative to the general population. So in this case, you would have a sample of PhD students and you compare their mean stress level to the average stress level in the general population. And if you find that there are significant differences, then you would conclude that your sample actually comes from a different population with a different mean. And therefore, PhD students do experience significantly greater amounts of stress compared to the general population. So we're actually going to learn to perform two different tests that are similar, but are used in different situations, both in a single sample scenario. And the test that you choose will depend on whether or not you know sigma. And again, sigma is the population standard deviation. So if sigma is known, you would use a single sample z-test. And here is the formula. And your critical values will come from the z-table that we talked about in chapter 8. However, if sigma is unknown, then you would use a single sample t-test. And here is the formula. And now your critical values come from a different table, the t-table, that we'll talk about more in this lecture. Okay, so we're going to begin by talking about single sample hypothesis testing when sigma is known. Okay, so I think the best way to learn is to just jump in, get our hands dirty, and run a hypothesis test from start to finish. And of course, we'll be using the same 5 steps that we introduced in the previous lecture. So step 1, write the hypotheses, the null, and the alternative. Step 2, determine the critical value or values associated with your alpha level. Step 3, compute the test statistic using the data in your sample. Step 4, evaluate the null, and that requires comparing the test statistic in step 3 to the critical value in step 2 to see whether or not your test statistic has made it into the rejection region. And if it has, then you reject the null hypothesis, otherwise you fail to reject. And finally, step 5 is simply stating the conclusion that implies restating either the null or the alternative, depending on whether or not you rejected the null. Okay, so let's consider the following scenario. Suppose we have a population of student exam scores with a known mean, mu, of 75 and a known standard deviation, sigma, of 10. We take a sample of 30 students who received tutoring, and the sample mean x bar of their scores is 78. We want to test if the sample mean of tutored students is significantly different from the population mean using an alpha of 0.05. Let's analyze the problem. We are going to be comparing a single sample of tutored students to some known population. And so therefore, this requires a single sample test. And importantly, we are being given the sigma, the population standard deviation. Therefore, it's going to be a single sample z-test. And now, had this been exactly the same problem, but without sigma, if we were not given sigma, then we would use the single sample t-test, which will be covered later in this lecture. And also, based on the wording of the problem, we are going to run a two-tailed test because we want to test if the sample mean of tutored students is significantly different. That implies it could be less than the mean, maybe tutoring makes you worse, or larger than the mean, maybe tutoring makes you better. We are interested in both possible outcomes, therefore it's going to be a two-tailed test. Okay, so then step one is to state the hypotheses. The null, H subscript O, should sound something like this. The mean of tutored students is not significantly different from the population mean. In words, in symbols, mu of tutored, the mean of tutored students is equal to 75 because that is the population mean that we are comparing the tutored students against. And now the alternative, H subscript 1, the mean of tutored students is significantly different from the population mean. Mu of tutored is not equal to 75. We are not specifying the direction of the difference because we are running a two-tailed test. So step two is going to be to find the critical value or critical values. So because we are running a two-tailed test, we are going to have two rejection regions, one above the mean and one below the mean. And because we have two rejection regions, there will also be two critical values, a positive critical value above the mean and a negative critical value below the mean. Okay, so how do we find the critical values? So remember, we want to take alpha, which is 0.05, we're given that in the problem, and divide by number of tails. There are two tails, so 0.05 divided by 2 is 0.025. And so now we want to go into our z table and in the smaller portion column, find the value that comes closest to 0.025. And there it is. We have that exact value. And now we want to pull out the corresponding z-score, and that is our critical value. So the critical value, values in this case, there are two, is plus minus 1.96. So positive 1.96 in the right tail and negative 1.96 in the left tail. So our test statistic has to be above this value or below this value to make it into either one of the rejection regions if we're going to reject the null hypothesis. Okay, so step 3 is the test statistic. And we briefly looked at the formula in this situation at the beginning of the lecture. Here is the formula for the test statistic to get the critical z-value. And it's basically a z-score. So x bar, that's the sample mean, 78, minus mu, the population mean, 75, divided by the standard error of the mean. That's what this symbol is. And the standard error of the mean is something we talked about briefly in the last lecture. This is the standard deviation of the sampling distribution. And the formula for the standard error of the mean is sigma over the square root of n. So if we were comparing a single score to a population, then we could just do a z-score using the population sigma. But because we're comparing a sample mean, we have to use the sampling distribution of the mean. And so basically it's a z-score, but in the sampling distribution. Okay. And so we have all the values that we need to plug into this formula. So x bar is 78 minus mu 75 divided by sigma over square root of n. So sigma is 10 divided by square root of n, sample size 30. That gives you an obtained z value of 1.64. Okay, so step 4 is to evaluate the null by comparing our obtained z value, the test statistic, to the critical z values. And so recall our critical values were plus minus 1.96. Our obtained z value is 1.64. And so it looks like we do not make it into either of the rejection regions. We don't exceed either critical value in either direction. And because of that, we fail to reject the null hypothesis. In step 5, having failed to reject the null, we can restate the null, which is that the mean of tutored students is not significantly different from the population mean. So in the last section, we learned the single sample z-test, which we use when comparing a single sample to a population with a known sigma. In this section, we're going to talk about what happens when sigma is unknown, and now we have to use a different test. So in many situations, we are not going to have access to sigma, the population standard deviation. And when that happens, we have to run a single sample t-test. And what we're going to do in the single sample t-test is we are going to estimate sigma by using S, which is the sample standard deviation. So again, we're estimating sigma, the population standard deviation, by using the standard deviation of our sample. And so if you look at the formula for the single sample t-test, it is almost identical to the single sample z-test, the only difference being in the denominator we are using S, the sample standard deviation, instead of sigma, the population standard deviation. And when we use a t-test, now we have to get our critical values from a different table called the t-table. And we'll talk more about this here in a few slides. Okay, so let me talk a little bit about why we use a different table of critical values when we don't have sigma, and some of the challenges that arise when using S to estimate sigma. So again, in a t-test, we're estimating sigma using S, the sample standard deviation, and estimates are not going to be perfect. And so when we're estimating the population standard deviation using the standard deviation of our sample, we are typically going to underestimate sigma. And the reason for that is because the population is typically more diverse than the sample. The population typically contains more extreme scores than our little sample. So most of the time, S is going to underestimate sigma. So one important factor in determining the quality of that estimate is the sample size. So if you have a very large sample size, then S becomes a good, reliable, unbiased estimate of the population standard deviation sigma. However, if your sample size is small, then it's not a very good estimate. And the smaller the sample size, the worse the estimate becomes. And so again, the problem that we're dealing with is that we're estimating sigma, the estimate isn't perfect, and the quality of the estimate depends on the sample size. So then the solution that we're going to employ is we're going to use a different distribution for the sampling distribution called a T distribution. And the T distribution is going to allow us to compensate for the greater uncertainty that arises when we use S, the sample standard deviation, to estimate sigma, the population standard deviation. So the shape of the T distribution is not stable. It actually changes, and it changes based on the sample size. And so if you have a large sample size, the shape of the T distribution begins to resemble the shape of the Z distribution. However, if you have smaller sample sizes, the T distribution becomes flatter and more spread out. And when the distribution becomes flatter and more spread out, the critical values are pushed further away from the mean. And this makes it harder to reject the null hypothesis. So the logic is if we have a small sample size, a small sample size will result in a poor estimate of sigma. And to compensate for that uncertainty, we're going to use a different distribution that's flatter, that's more spread out, that's more conservative, that will make it harder for us to reject the null hypothesis. All right, so the critical values are going to come from the t table, from this table here. For the single sample t-test, and really for any t-test. We will cover other t-tests later in the course. So this table, the innards of the table, are all critical values. And so the critical values conceptually should be thought of in the same way as the critical z-values. They serve the same role in the context of your hypothesis testing process. But now they're called t-values and they come from a different table. So how do we use this table? So first, you want to find the appropriate row, and this is going to be your DF, or degrees of freedom. And degrees of freedom for the single sample t-test is going to be n minus 1. So take your sample size, subtract 1, and find the corresponding value in this DF column, and that gives you the row that you're going to use. Now, if your DF value is not listed in the table, if it falls in between two other values, for example, if your DF value is 38, it falls between 40 and 30, in that case, you always want to go up and take the smaller of the two DF values. Okay, so you find your DF value, that gives you the row. And the column will be your alpha value. Now, unlike the critical z values where we divided alpha by number of tails, this table already does that for you. So notice there are two rows of alpha values, one row for the one-tail test and the second row for a two-tail test. So figure out if you're using a one-tail test or two-tail test and find the appropriate alpha value, and that gives you the column. And so now you have the row, you have the column, and that is gonna give you your critical t value or t values. Okay, so just a little bit of practice using the table. So for example, suppose we have a sample size of 6. Our alpha is 0.01. Our alternative hypothesis is mu of sample is less than 15. That implies a one-tail test looking at the left tail below the mean. And we want to find the critical value for this study. So degrees of freedom is going to be n minus 1, sample size minus 1, so 5. So that will be our row. Our column is going to be the one-tailed alpha value of 0.01, so right there, which gives us a critical value of 3.365. But because we are looking at values below the mean, the left tail, mu of sample is less than 15, you have to make that value negative, right? The values in the table are all positive, but your critical value could be positive, negative, or positive and negative if you're using a two-tailed test. Now, there's also kind of a proper way of writing these critical values. And so you would say T subscript alpha parentheses DF equals your critical T value. So in our case, it would be T subscript alpha 0.01 parentheses DF, that's 5, equals negative 3.365. That's our critical T. Okay, so just one more example here. So suppose we have a sample size of 9. Our alpha is 0.05. The alternative hypothesis is mu of sample is not equal to 25. That implies a two-tailed test. And we want to find the critical value. So our degrees of freedom is going to be n minus 1. So 9 minus 1 is 8. And so that's going to be our row. And the column will be a two-tailed alpha value of 0.05. So right there. And that gives us a critical value of 2.306. But remember, because it's a two-tailed test, there are actually two critical values, a positive and a negative, so plus minus 2.306. And writing it the fancy way, T subscript 0.05, that's our alpha, parentheses DF equals plus minus 2.306. Okay, so let's practice the entire process from start to finish using our 5 steps of the hypothesis testing process. And again, we're using the same 5 steps. Now, of course, in step 2, our critical values come from a different table, the T table. And in step 3, we're using a slightly different formula compared to the Z-test. But conceptually, nothing has changed. The logic of the hypothesis testing process is still the same. Okay, so let's consider the following scenario. Dr. Zen created a pill to reduce the number of anxiety attacks of people with anxiety disorder. He gives the pill to 25 people and records the number of anxiety attacks they have in a month. He finds that they have an average of 10 attacks with a standard deviation of 5. The average number of anxiety attacks that people with anxiety disorder have per month is 16. Does Dr. Zen's medication reduce the number of anxiety attacks, setting alpha at 0.05? Okay, so let's analyze the problem. We are being asked to compare a sample of people who took this pill to some population. So that's going to be a single sample test. We are given the population mu, 16, but we are not given sigma, the population standard deviation, and therefore it's going to have to be a single sample t-test. Now, also looking at the wording of the question, we're being asked, does the medication reduce the number of anxiety attacks? And that implies a directional test, a one-tail test, specifically looking at the left tail, below the mean. Is the number of anxiety attacks less than the mean in people who took the pill? So a one-tail test looking at the left tail of the distribution. Okay, so the hypotheses. The null should sound something like this. There is no significant difference in the number of anxiety attacks had by people who took the pill compared to the average person with anxiety disorder. Mu of pill equals 16 because that is the population mean. And the alternative hypothesis is that people who took the pill have a significantly lower number of anxiety attacks compared to the average person with anxiety disorder. Mu of pill is less than 16. Okay, so step 2 is to find the critical value. So we need degrees of freedom. That's sample size, which is 25, minus 1, so 24. That will give us the row, and the column will be the alpha value for a one-tailed test. So this is our row. Here is our column, alpha of 0.05 for a one-tailed test. So our critical value is 1.711. But because we are operating to the left of the mean, below the mean in the left tail, this is going to be a negative value. So negative 1.711 is the critical value. And so then the test statistic, step 3, this is the formula. So x bar minus mu over the standard error of the mean, which is s divided by square root of n. So we have all of these values in the problem. X bar, that's the sample mean, so 10 attacks. That's what the people who took the pill had. Minus mu, that's the population mean, so 16. Divided by standard deviation over the square root of n. The standard deviation is 5. We're given that here. That's the sample standard deviation, s. Divided by the square root of sample size, the square root of 25. That should give you negative 6. So negative 6 is our obtained t value, the test statistic. All right, so then steps 4 and 5. Step 4 is to evaluate the null hypothesis by comparing our obtained t value, which was negative 6, to the critical value, which was negative 1.711. Our obtained t value clearly exceeds the critical value and makes it into this tail, into the rejection region, and therefore we can reject the null hypothesis. And now, having rejected the null hypothesis, we can state the conclusion as the alternative hypothesis, and that is that people who took the pill have a significantly lower number of anxiety attacks compared to the average person with anxiety disorder. Okay, so in this section, we're going to discuss some factors that will influence the likelihood of you rejecting or failing to reject the null hypothesis when running a single sample t-test. All right, so what has to happen in order for you to reject the null hypothesis? Well, for that to happen, your obtained t-value has to exceed the critical value in either the positive or the negative direction. Okay? So in absolute terms, your t-value has to be larger than the critical value. And so the t-value and the critical value, those two values together will determine whether or not you reject the null hypothesis. So let's begin by talking about the factors that determine the magnitude of the obtained t-statistic. Okay, so first, the difference between x bar and mu, which is the numerator of the formula for the t-statistic. And so the larger this difference in absolute terms, the difference between the sample mean and population mean, the larger your t-statistic is going to be. Like mathematically, that has to be the case. And conceptually, this should also make sense. The larger the difference between the sample and the population that you're comparing the sample against, the more likely it's going to be that there's a significant difference between that sample and population, and that you reject the null hypothesis. Okay, so next we have the sample variability as measured by S, the sample standard deviation. And so mathematically, as this number goes down, the t-statistic has to go up. That's just going to be true mathematically. But let's also try to understand conceptually why less variability in your sample increases the probability of you rejecting the null hypothesis. So let's say you have a sample of students who received extra tutoring for some course, and you want to compare their average exam score to some larger population of students who were not tutored. And let's say the sample mean is 75. Well, if the variability in that sample is large, that means the scores are all over the place. Some way above the mean, some way below the mean. And because the sample is so messy and noisy, it becomes harder to understand what is really going on and to detect the true effects of the tutoring. Conversely, if the variability is very low and all the scores are clustered tightly around the mean, well, now you have more confidence in what the true effects of the tutoring may be. Okay, so next we have n, the sample size, which is also a part of our formula for the t-statistic. And mathematically, as n goes up, the t-statistic also becomes larger. Now, conceptually, having a large sample size is always good because a larger sample size will give you a more precise, more reliable estimate of the population parameters. So larger samples are always going to be more reliable. And also, your sample size determines the degrees of freedom, which determine your critical values. And so having a larger sample size will shift your critical values in a favorable direction and make it easier for you to reject the null hypothesis. Okay, and so next we have your significance level, or your alpha. And so alpha does not have any direct effect on the t-statistic, but it does affect your critical values. And so a larger alpha means fatter tails, means the critical values get pushed in closer to the mean. So the critical values are not as large, and therefore your t-statistic does not have to be as large in order to exceed the critical value and reject the null hypothesis. Finally, whether your test is one-tailed or two-tailed. So remember, in a two-tailed test, we split alpha, with half of alpha going into one tail and half in the other tail. So in a two-tailed test, your rejection regions are smaller, and therefore the critical values are further away from the mean, making them larger, making it harder to reject the null hypothesis. By contrast, in a one-tailed test, all of alpha gets poured into your tail, which pushes the critical value closer to the mean, so the critical value is not as large. And so it will be easier for you to reject the null hypothesis if you're using a one-tailed test, but only if your effect is in the tail that you specified. If your effect is in the other tail, you can't touch it. And so that's the trade-off. Okay, so in the last section of this lecture, we're going to talk about something called confidence limits, or confidence intervals. Okay, so what are confidence limits? Well, let's take X bar. X bar is the sample mean, and recall that X bar is an estimate of a population parameter, the population mean, mu. So X bar is an estimate of mu. Now, X bar is known as a point estimate because you are estimating mu with a single value, a single data point, X bar. Now imagine, instead of giving a single point, X bar, you give a range of values that you believe likely contain the population mean. And so that range of values is called the confidence interval, and that's referred to as an interval estimate. So by analogy, let's say that I witness a crime and the police are interviewing me about the perpetrator. And suppose they ask me, well, how old did the person look? And imagine I say, he looked 37 years old. That would be a point estimate. And that's kind of strange. People probably would not give a point estimate in that situation. Instead, they would likely give an interval estimate. I would probably say, well, he was somewhere in his 30s, maybe between, 35 and 39. Okay, so that's an interval estimate. And now the other component here is that we can add a confidence level. So like, how confident are you that the value that you are estimating falls within this range of values? So for example, if we have a 95% confidence interval, What that means is that we are 95% confident that the true population mean falls within that interval of values. Okay, and so here's just a visual representation of what we're talking about. So let's say you have some population. The population mean is mu. And then you have a sample, and the sample mean is x bar. And so x bar is a point estimate of mu. Now, what we can do is we can add a confidence interval that is centered on x bar. And if, for example, if we have a 95% confidence interval, then what we're saying is that we are 95% confident that the true population mean falls somewhere within this interval of values. Now, something to note is that there's going to be a trade-off between confidence and precision. So suppose we want more confidence. Let's say 95 is not enough. We want 99% confidence. That's fine. You can have more confidence, but what's going to happen as a consequence is that your interval becomes larger. So the estimate becomes less precise. And so there's always going to be this trade-off between confidence and precision. If you want more confidence, you get less precision, and vice versa. So there's no free lunch. There are always going to be trade-offs. So here's how you compute the confidence interval. So step one is going to be to get a critical t value from the t table. The rows are going to be degrees of freedom, so that's n minus 1 for the single sample t-test. Now, the alpha value, that's going to be the column, that's going to be linked to your confidence level. And so here's how it works. So for example, if your confidence level is 95%, then you subtract 0.95 from 1, and that gives you alpha, so 0.05. If your confidence level is 99%, then you subtract 0.99 from 1, and then your alpha is 0.01. Again, so the idea is take the confidence level as a decimal, subtract that from 1, and that gives you the alpha. And also for confidence levels, the alpha is always going to be two-tailed. Okay, always two-tailed. Don't worry about the one-tailed values. Next, we want to compute the lower and the upper limits that define the confidence interval. And here is the formula. So for the lower limit, it's going to be x bar, the sample mean, minus the critical t value from step 1, times standard error, which is standard deviation divided by the square root of n. And the upper limit is x bar plus the critical t value times standard error. And so that gives you the two values, the lower and the upper limit that define the interval. And then you format your answer in the following manner. You're going to say mu, that's the population mean that you're estimating, is greater or equal to the lower limit and less than or equal to the upper limit. So you're basically saying that the mu is somewhere between these two values. And finally, the way that you would phrase your answer is you would say that we are some percent confident, whatever your confidence level is, that the population mean of the dependent variable, whatever it is that you are estimating, falls between these two values the lower and the upper value. Okay, so let's consider the following scenario, and we'll do an example of how to compute the confidence intervals. So a national survey indicates that the average college student donates $22.20 per year to charity. A social psychologist develops an intensive global citizenship workshop designed to increase empathy and charitable giving. She recruits 30 students to take the workshop. 1 year later, she tracks their donations and finds that they gave an average of $44.40 with a standard deviation of $5.50. So compute the 95% confidence interval for the true population mean of donations for students who take this specific workshop. Okay, so let's solve this problem and compute the 95% confidence interval. So step one is to find the critical t value from the t table. Our degrees of freedom is going to be n minus 1, so 30 minus 1 is 29, so that's going to be our row. The column is going to be the alpha value that is determined by the confidence level. Our confidence level is 95%, so our alpha is going to be 0.05, 1 minus 0.95. And for confidence intervals, we always get the two-tailed value. And so that gives us a critical t-value of 2.045. Step two will be to compute the upper and lower limits of the interval. So the lower limit is going to be 44.4, that's x bar, that's the mean of the sample, minus the critical t from step one, times the standard deviation of the sample divided by the square root of the sample size. And that gives us 42.36. And now the upper limit is going to be x bar plus the critical t times the standard deviation of the sample over sample size, and that gives us 46.45. Now we can format our answer in the following way. We can say mu is greater or equal to 42.36, the lower limit, and less than or equal to 46.45, the upper limit. And finally, we can state our answer in words. We are 95% confident that the true population mean of charitable giving of students who took the workshop falls between 42.36 and 46.45.